Okay, this is going to be a relatively short video. I wanted to do two videos back to back because on Thursday I put out the video where I had you do a little bit of work. I wanted you to tell me the number of protons and neutrons from tungsten that had a mass number of 184 and francium if it had a mass number of 223. So I wanted to give you the answers to those relatively soon after I gave you the assignment. But we won't be quizzed over the other information on this video until next week. That will be the 11th through the 15th. So you might want to watch this video again on Monday. So the deal with that little homework, I hope you're doing this. I really honestly hope that you guys are going along with these videos, because this is how you're going to learn this stuff. It's easier for me to do this in the classroom. I'm doing the best that I can with these videos. I've changed around my PowerPoint presentations. So I do hope you're taking advantage of this fine cinematography that I'm giving you guys. So if you have this paper and you did it, get it out and let's go through it. If you haven't done it yet, maybe you could pause the video and do this, because it's much more beneficial if we go through the answers after you've tried to get them yourself. So if we find tungsten on the periodic table, tungsten's symbol is a W. I don't know, it's a W. But if you find it, it is in the transition metals. That's those 10 short families in the middle here. Tungsten's right down there. When you look at tungsten, you see that its atomic number is 74. That means the atomic number is just another way of saying the number of protons, right? So should be a 74 right there. And then if you know that you have a mass number of 184, that is, by definition, mass number is number of protons and neutrons. So let's do P plus N. So if 74 of them are protons, everything that's left has to be neutrons. We should be 110 there. Francium. Francium is the very bottom element of the alkali metals. It is the most reactive metal. It's so reactive that it can't be by itself long enough to even get a picture of it. It's only found in compounds. Anyway, so francium has an atomic number of 87. Means it has 87 protons. When you take its mass number of protons and neutrons, and take the protons out, you're going to end up with number of neutrons as 136. Copper. Copper is a transition metal. It's found in the top over to the right-hand side, right by zinc. Here's something interesting. Copper, silver, and gold are all found in the same family on the periodic table. You guys can see this. So we've got copper, silver, and gold. And those are the three best conductors of electricity, and they're all in the same family. Families on the periodic table have things in common, just like you, members of your family, have things in common. Lots of people in my family have a gap because we're all related, and it's a trait that we share. The coolest of us have gaps, and then there's my sister. She's not cool. She's not. But anyway, so copper's atomic number is 29. So 29 from 65 is going to be 36. Hope I'm doing my math right. You guys can check me. But basically, if I add my protons and my neutrons together, that's going to give me my mass number for this isotope of copper. And we're going to talk about isotopes in a minute. Chlorine is a halogen. It's over the second to the last family on the periodic table. Fluorine, chlorine, bromine, iodine. Those are all the halogens. Halogens are always found in salts. NaCl, chlorine is a halogen, that's salt. A metal and a halogen makes a salt. As I said before, you know what you get with a salt, 10 to 20. Chemistry joke. Anyway, chlorine has 17 protons. All atoms that have 17 protons will be chlorine atoms. If this particular atom of chlorine has 36 protons and neutrons, then we're going to end up with 19 being neutrons. Silicon, however you want to say it, is a metalloid. It's found on the zigzag line there, kind of the rough dividing line between metals and nonmetals on the periodic table. Some of the elements that touch that zigzag line are known as metalloids, which means they kind of have metallic properties, they kind of have non-metallic properties. There's other things they have in common. They're semiconductors, which means they conduct electricity only under certain conditions. But silicon happens to have 14 protons, and this particular isotope of silicon has 14 neutrons as well. This, when the protons and neutrons are close to or equal in number, that often indicates a stable nucleus. That nucleus is happy. It's not going to do anything to stabilize itself because it's already stable. That's one rule you can kind of follow. If we have a huge difference between protons and neutrons like we do with francium up here, that shows a very unstable nucleus and radioactive decay is going to result. 92, the last element that is found naturally in the universe is uranium. Uranium's atomic number is 92. Uranium is found down here in the actinides. This family here is the actinides, or this period is the actinides. There's 14 families. And if we take uranium-238, take 92 of the protons out, it's going to have 146 neutrons. So I hope that I hope you guys got this right. I hope that you tried it. Now, let's go on to a little bit more before we leave the nucleus. I tried and I tried and I tried, and I couldn't get these to come up separately. So I'm going to show you a lot of words to begin with, and I apologize. Pause it if you have to write this down, but let's talk about this. So the nucleus is what we've been talking about. We found out that there's over 200 particles in the nucleus, but we are really only concerned with protons and with neutrons. Protons are made up of smaller things called quarks, and neutrons are too, and yada yada. Most of the mass of an atom is found in the nucleus. 99.9% of the mass of an atom is in the nucleus. The rest of the atom is just this area that we call the electron cloud that doesn't have much stuff in it. It has very small particles flying around. If you look at it this way, if the atom was an entire baseball stadium, the nucleus would be a marble in the middle of it. Let's make it a little bit more, let's say it's a golf ball. Okay, think of it this way. If you could lift up that entire baseball stadium, okay, take it over and put it on a scale, and it weighed 10 million pounds. I don't know what a baseball stadium weighs. Let's make it simple. Let's say it weighs 100 grams. Okay, this is a model. It weighs 100 grams. And then I take the baseball stadium off of the scale, I put it back, and I pick up the nucleus. I leave the stadium there. I just pick up that golf ball that's in the middle, and I put that on the scale. Remember, the whole stadium weighed 100 grams. That golf ball would weigh 99.9 grams. The whole rest of the stadium weighs 1/10 of a gram. That's how concentrated and dense that nucleus is. That's why Rutherford was so surprised to see those alpha particles bouncing back, but they were hitting something that was very, very dense and positively charged. So here's what I want to look at. So when you're looking at the nucleus, you count the protons to determine the identity. I hope that you guys have that down by now. But we have a little thing called an isotope. Okay, so I want to talk a little bit about isotopes. So let's draw the nucleus of an atom. There we go. Boom. Nice and round. I'm going to place into that, if you'll notice, that the red dots are going to be protons. So I'm going to put into there 1, 2, 3, 4, 5, 6 protons. Look at your periodic table. What element do I have? Got carbon, right? This particular, so if we have carbon, excuse me, that means my atomic number is going to be 6. All right. Now, let me go ahead and put in some neutrons. This particular one that I'm talking about has 1, 2, 3, 4, 5, 6 neutrons. I add those together, my 6 protons and my 6 neutrons, to get my what? My mass number, right? So the mass number for this is 12. This is an isotope of carbon that we call carbon 12. And I'm going to show you on the next page how to represent these in the right format with symbols and stuff. Now let's go ahead and go to, let me change my pen color back here. Let me go to another nucleus. So we've got another nucleus. I've drawn the circle, and I've put in the same number of protons. So I'm dealing with atomic number of 6. So I still have an atom of carbon. The atomic number, or the number of protons, tells me who the element is. This guy's carbon, this guy's carbon, but they're slightly different because this carbon over here has 1, 2, 3, 4, 5, 6, 7. Is that it? Back it up. 7 neutrons. So this is, we have the same atomic number if it's the same element, but we have a different number of neutrons, so we have a different mass number. 6 plus 7 is, need this thing to go away. 6 plus 7 is 13. This is an isotope of carbon known as carbon 13. Let me show you how these are represented. Instead of drawing these pictures out, let me show you how we represent it. We have another isotope of carbon known as carbon 14. Carbon has 3, carbon 12, carbon 13, carbon 14. Carbon 12 is by far the most abundant. Carbon 14 is unstable. It's radioactive. If you've heard of carbon dating, you will know that they use, this is the isotope that they're using to determine how old something is. Long story, we're not going to get into that. But let me draw an atom of carbon 14. All right? So 1, 2, 3, 4, 5, 6. That makes it carbon. Those my nasty little plus marks there. I apologize. Should have made those red because my last one was red. But now I'm just going to draw zeros for the neutrons because they're neutral. I drew pluses for the protons because they're positive. 1, 2, 3, 4, 5, 6, 7, 8. This would be a representative of the nucleus of a carbon 14 isotope. There's 2 ways we can represent this. We can put C, the carbon symbol, a dash, and 14. The mass number goes here. That's one way to do it. Another way is put the symbol for carbon, C, and in the upper left-hand corner, we put the mass number. Now, let me show you guys something. I wish that I had a way to make this pen thicker, but I don't. So let me go, let's go to red. So draw this out. We're going to use carbon as an example, but this is any element. The symbol is written, and then there are things that are placed in the upper right-hand corner, the upper left-hand corner, and the lower left-hand corner. They're always placed in those places. In the upper left-hand corner, you will always find the mass number. If they want you to know the specific mass number, they will put it in the upper left-hand corner. If they just want you to know that it's carbon, they'll just put a C. Sometimes down here in the lower left-hand corner, you will find the atomic number. I personally feel like that is redundant because I know the atomic number if I know the symbol. Carbon is 6. You'll never see me type it this way on a test or anything because I don't know how to do a superscript and a subscript in the same vertical space because I come from a simple people. Then in the upper right-hand corner, we're going to be getting into this little bit, is where you're going to find the charge. You find the charge by comparing the number of protons and the number of electrons. We haven't really talked about electrons yet. We've stayed within the nucleus for now. But when we get into the electron cloud or outside the nucleus, I'll show you how to figure charge. So if there's nothing written here, it's neutral. If it has a charge, you put the charge here. So let's do another example. Let's say that let's go back to chlorine. All right, and I'm going to talk about chlorine, the isotope 35. So I'm telling you that I'm talking about a specific isotope. And so that means that it has 35 protons and neutrons. It's chlorine, so we know that that is its atomic number. And then sometimes chlorine, a lot of times chlorine, is going to steal electrons from somebody else, and it's going to have an extra electron, and its charge would be a -1. This tells you a lot of information. I've got chlorine. This tells me it's chlorine. This tells me it's chlorine. It tells me it's the isotope that has 17 protons and 18 neutrons, and this particular one has stolen an electron and has a charge of -1. So that is stuff in a nutshell. I don't think we'll do more on isotopes later. That'll be the next video. But I hope that this helps you. And you can always go look up on Google. There's tons and tons of videos out there. They're not as cool as my videos, because I'm cool. But there's some really good ones. Tyler DeWitt, he's pretty awesome. He's the hairy armed guy that we talk about. Anyway, hope this helps. See you guys on the other side.